We've been talking about collisions when we have an object hitting the wall, or also when you have two objects colliding with each other. We imagine in a collision, two objects would be coming towards each other, they would hit, and they would bounce off of each other in opposite directions. If we consider these objects separately, then each particle feels an external force from the other, which is what is changing its momentum. So in that case, if we look at particle 1 is moving one way. Particle 1 feels a force from particle 2, essentially a normal force from the other object, and particle 1 is now moving the opposite direction. And so you have a change in momentum for particle 1. We could argue the same thing for particle 2. It's moving one way, it feels a force, it feels an impulse from this external force, and now it's moving the other way. However, if we consider both particles to be part of the same system, then these interacting forces are internal to the system. What this means is that if we have internal forces, we're including the action-reaction pair within the system. Basically, these forces are going to balance each other out. And when we're looking at our momentum, our change in momentum as an impulse, which is a force applied over time, this is true only for an external force. If we include both of these objects in our system, this interaction force is no longer an external force. And so in this situation, the impulse would be 0, the change in momentum would be 0. And if the momentum is not changing, then that means the momentum has to stay the same. It means that the final momentum, the momentum after the collision, would have to be the same as the initial momentum because the momentum is not changing. Again, this is true when you have forces that are internal to the system. When you have only internal forces and no external forces, momentum is conserved. We can see a more thorough derivation of this idea. Imagine you have a system that consists of 3 particles within that system. The total momentum of the system would be the momentum of one particle plus the next particle plus the next particle, on and on until you're adding up the momentum from every single particle in the system. In this case, you'd only add up P1, P2, and P3 because there's only 3 particles there to give you the total momentum of the system. If we apply Newton's second law and we say that we want to find the change in motion for each object, for each particle, and that the force is going to be that change in momentum. Basically, we're looking at our change in momentum, our mass times acceleration, as the sum of the forces acting on each particle to see how each particle will change its motion and change its momentum. What we realize is that all of the internal forces that we have forces between 1 and 2, we have forces between 2 and 3, and we have forces between 1 and 3. These are all internal forces because they're acting inside the system, and each one of these pairs of forces are equal and opposite. That's the whole point of our interaction forces. We have the equal and opposite reaction. And so when we're looking at the mass times acceleration, the change of momentum of each object, we're looking at the sum of all of the interaction forces plus the sum of all the external forces. But we see here that if we're counting up all the different interaction forces, if we count the force of particle 1 acting on particle 2, we'll also count the force of particle 2 acting on particle 1, and those will cancel out completely. We'll include the force of particle 3 acting on particle 1, the force of particle 1 acting on particle 3, those will cancel out completely. And what we see is that going around every single interaction force between neighboring particles, we'll see an equal and opposite reaction, and thus those internal forces will not affect the overall momentum of the overall system. However, when we look at external forces, here we have an external force acting on 2. There's nothing to balance that out. That will be a net force acting on 2. This force may then be distributed because 2 will push on 1, 2 will push on 3, and you may redistribute that force within the system, and the system itself will have a reaction to that external force. But that force will definitely influence the whole system. The same is true if you have an external force acting on 3. That will affect particle 3's other interactions and this force will be distributed throughout the system, but this force will act on the entire system. Thus, we see that the change in the total momentum is equal to only the net force applied to the system, only to the net external force applied to our system. And this result shows our particle model, what we've been talking about all along, where we treat objects as a particle and their motion, their interactions only as a particle. We see that the internal forces within an object, those internal forces between individual atoms, for example, do not affect the motion of the particle as a whole. If you push on an object, really you're pushing on a few atoms, and then that force ripples out through the rest of the object as the atoms apply the force to other atoms, which apply the force to other atoms, until you're applying a force to the entire object. But only your external force is affecting the motion of the object. The individual atomic bonds are all internal forces, and they don't change or affect the motion of the object. Thus, we just found that the change in momentum of a system is equal to the sum of the external forces that are acting on the system. If we have an isolated system means that the external force is equal to zero, that there's no forces acting on it. And if that's the case, if there are no external forces, then the change in momentum must be zero. And if the change in momentum is zero, we've seen before that this means that the change in velocity must also be zero, which means that the velocity is constant in a case where we have no external forces. We've seen that situation before when we talk about Newton's laws. So that's one thing that we look at when we are trying to decide what system we're talking about. If you have a rocket feels thrust from the rocket engine. And so in that case, it's not an isolated system. You have an external force. If you consider the momentum of the rocket plus the exhaust gases system, then the rocket accelerates forward as the gases are expelled backward. In that situation, that is an isolated system, and the change in momentum would be zero. We'll see in a later lesson in this module how to calculate that. An important point here, this is a Delta IV heavy rocket. You can tell from the blue sky behind it that it's blasting off from Earth, and thus it's not an isolated system because it would still be subject to Earth's gravity. When we talk about a rocket or the rocket plus gases system, we'd be talking about a rocket in deep space where it'd be away from any sources of gravitational force. In that situation, a rocket engine would still work. You would still have net zero change in momentum of the overall system. So to recap the conservation of momentum, we define an isolated system. An isolated system is a system in which the net external force is zero. When we have an isolated system, the change in momentum of that system is zero because external forces are needed to change the momentum, and we're defining this so that there are no external forces. Our law of conservation of momentum, then, says that the total momentum of an isolated system is constant. Interactions within the system do not change the system's total momentum. If we wish to write this mathematically, we can write it thusly. The total momentum at some initial point in time is equal to the total momentum at some final point in time. Similarly to our conservation of energy, when we could look at the energy of the system being constant, even as the energy changes forms, and we could look at the energy at any point in time along that evolution and say that the energy is always a constant, the overall energy is always constant. The same way here we can look at the evolution of the system typically before a collision and after a collision, and we know that the momentum before the collision must equal the momentum after the collision.